International Light, and today in this presentation we're going to be discussing measuring what we'll call short-lived light, flashlight, pulsed light, strobe light, and any phenomenon that just doesn't last for a long period of time and creates some challenges to actually capture that signal. So we're going to start in. So our goal here, we really want to capture about 90% of the flash and pulse use cases. Again, as we'll see later, we'll discuss that it is difficult, but with the tools, the meters, and the software we have in place, the vast majority of the common use cases we could capture pretty readily. For some faster or higher frequency, as we'll discuss, it might require a little knowledge beyond this presentation, but by and large, a lot of the flash measurement that we've come across over really decades we'll be able to capture here using these methods. So here's just the agenda. We're going to go through the basic problem statement. Excuse me. We're going to discuss a little bit about the concept of energy versus power. We're going to talk about all the sources that we commonly see that are short-lived light, flash. And then we're going to get into the actual meters themselves and the software and how we measure using the meters and the software. And then we have some examples, and through other materials we'll be posting, we'll actually have video capture of some of those examples in real life, if you will. So here's the problem statement. It's measuring these short-lived lives or flash or strobes is tricky. And the kind of 4 sub-bullets here, it's you need to coordinate capturing when it happens. So it's usually an abrupt signal. So your start of capture and duration of capture really need to be synchronized to what may be a randomly occurring signal. You need to go at high speed. You are sampling what could be something on the order of tens or hundreds of microseconds long. So you want to be able to adequately sample that to get a good profile. And you also want it's pretty good dynamic range. So all the meters here will range and be able to basically walk up and down the amplitude of those signals. And the fourth, kind of the most important, is you want to be able to comprehend the results. As you have a measurement circuit, it is representative of the real life physical occurrence, but it's not always a perfect match, and you need to understand where there could be a difference and what that difference is. So a little more on that later. So energy versus power, we're going to have a few slides on this, but energy is the integral over time of power. And there is electrical power and radiant power. We've got an example slide coming up with the caution, don't confuse these. Again, we'll see that. I think it's the next slide. For these flashed and pulsed lights, energy can be reliably measured. That's that integral, but power in some cases cannot. And that harkens back to that 4th bullet on the prior slide where we said the physical world can sometimes differ from the measurement world. And again, we have a little more on that later. In most cases, you are measuring the energy of the pulsed light. So you're in good hands, and when you want to look at the actual power levels or peak power, in some cases you need to do a little more work. We'll talk a little bit more about that later. So here again, energy is the integral of power. So this blue line here is the flash profile. This is the relative peak of that power. We're going to talk more about that later. This is the profile, the area under the curve. People might be shaking a little bit thinking back to calculus 1. The area under the curve, the integral, that is your energy. And this here is a single pulse. It's got 1.27 joules per centimeter squared. We'll talk about units shortly. If I measured 3 of those pulses on a constant x-axis relative to time, and if these pulses were separated here by approximately half a second, the pulses would look a lot different because they're just momentary spikes in time on a longer time axis. Whereas this time axis is 2 milliseconds, this one is a whole second. So this is what you would expect to see represented in the physical world. It does not live very long. And as you'll see in the meters and the applications, we can capture a single pulse that's dragged out with a lot of detail, or we could also measure multiple pulses in a string. So this one here, this is, we put this here is several times. People who were new, in a lot of cases, measuring ultraviolet curing or disinfecting sources, they will typically grab a meter and start measuring light, and they will be looking to read on the meter what the flash lamp controller was spec'd at, in this case 505 joules per pulse. So they'll pulse their system, they'll grab a reading, and they'll say, I'm expecting 505 joules, and I'm getting a very different answer. The reason that is that, here again, we start with electrical power, and then we have energy. This is in terms of joules. Joules is a measurement of energy. It's watts over time. So there is energy, electrical energy, going into this meaty lamp or light source, or discharge light source typically. And coming out of that light source is a resulting radiant energy. And that is measured in joules per centimeter squared typically. And a pulse would be joules per centimeter squared per pulse. And in this case, the 505 joules per pulse of electrical energy at a particular distance, that's important too, creates 1.27 joules per centimeter squared. And distance here for this particular system. And so your meter reads 1.27. Again, people who are new to this, what's important when you're curing or disinfecting is the amount of radiant energy at your working distance. And that's what the meter is going to read out. It's related, but certainly not equal to the electrical energy. Some of the common power and energy units you'll come across for UVC disinfection and curing. The power units are watts per centimeter squared, again, at a working distance, and the energy units are going to be joules per centimeter squared. For camera flash, your power units are lux or lumens per meter squared, and your energy units is lux seconds. And warning and indicator strobes, these are your wingtips, these are your fire alarm strobes. You got candela per meter squared, and then candela seconds per meter squared. And then laser safety, a lot of them are spec'd at watts per centimeter squared of power level and joules per centimeter squared. These are just examples. You can take any one of these power units and energy units and turn it into multiple other units by using conversion factors. Power and energy we've been talking about up to this point, but they are known by other names just to make things a little more confusing. But power, you will see it referenced as a radiance, its intensity. If you're doing UVGI applications, disinfection, there's a fluence rate, and then the energy is exposure, its dose, its fluence. So it's kind of a keep. You'll see these. Don't get confused. You could map these back to either power or energy. So we talk about energy. An interesting topic is discharge sources for flash versus LED flash. Traditionally and currently, there's large part of the market in the disinfection and curing market that are discharge flash. And that those are abrupt, brief, high-powered outputs. They're like the traditional camera flash, very bright for a very low amount of time. The pulse duration is typically tens of microseconds. LED flash, and these have pretty much taken over a lot of the indicator lights out there, like your airplane safety indicators or strobes and your fire safety indicators. It's a more gradual, longer, lower power output, but as we'll see in the graph on the right, the energy is the same or similar. And that pulse duration is typically on the order of hundreds of milliseconds as opposed to tens of microseconds. But the punchline here is the energy for like applications is usually the same. Because remember, energy is area under the curve. And in this picture here, the orange, if you all see that as orange like I do, is a discharge flash. It goes super high and then it decays quickly. And the blue is an equivalent LED flash. And these are actually, we measured these. These are the same application of a warning strobe. The manufacturer started with a discharge flash and moved over to an LED flash. And did a lot of the work to make sure they were equal. They had the same energy. And for the indicator lights, it's all about the amount of energy that the human eye picks up on to perceive what is a warning. Examples of short-lived light sources, and we measure all these and many, many more, but these are pretty common ones. Pulse xenon sources, UV disinfection, UV curing. Airplane wing strobes, these are wing strobes example, but they're strobes on top of the plane, underneath the plane. Fire alarm strobe, so around where the fire alarm goes off in the hotel, there's also a strobe light or building. Camera flashes, discharge flash, and LED flash, like your smartphones. And another one, it's a little different category, but it's called audience scanning. So you go to that rock concert and there is a laser emitting light and scanning the audience. It's just moving at high speed. And the reason this is a short-lived life is the safety folks involved here want to know how much power and energy are present when the laser scans over your eye. And they're looking for a quarter second or a half second shot in time or moment in time. And this slide here just depicts what the various signals look like for those light sources. So the time scale, they're zoomed. You see here, these are all different time scales. The xenon flash, this is on the order of milliseconds, or say 1 millisecond in time that it lasts. LED strobes, remember they're lower power but live longer. They could be on the order of hundreds of milliseconds. Fire strobe, typically often an LED strobe nowadays, usually briefer, higher power. Camera flash, similar in shape to the xenon flash. Well, it could be a little longer in time. All depends on what your flash settings are. And then the laser scanning, again, the safety is about 250 milliseconds. And that's what they're estimating when the laser scans your pupil. That's how long it will take. On the right here, they're all the x-axis is all fixed at 1 second. So you can see that the xenon flash, the discharge flash, is a moment in time. The LED signals last a little longer. And measuring those is either different or similar. As we'll see, we have some meters and modes where everything is done automatically for you. And there's also some software that drills down a little deeper and asks you to set some of these parameters. And so we're about to start rolling into actual examples. And this slide here talks to the various meters or applications. Got ILT 1000, 2400, 2500, 5000. And we've got a variety of applications that are either embedded in the meter itself for the 2400, 2500, or they're a piece of software that runs on a computer or laptop for any of these meters. This is the measurement method. This is the internal API used. If there's folks out here who a lot of folks write their own code to interface with the meters, because it's got a fairly extensive API. So they'll be familiar with these. If you are not, it's worth getting a hold of the API document that's up on the website to learn more about those. And then there's a flash detection method and what it detects. So I'm going to walk through these relatively quickly, and then we're going to see some examples coming up. But all the meters, they have a very simple start, stop, integrate mode. And this is akin to if you've been doing this for a while and you remember the ILT 1700, heck, you might even still have one hanging around. It was start your flashing source, hit start, hit stop, get answer. And that's what this one does. And it gives you the energy. We also have a firmware peak mode. So this, and FW peak, it stands for firmware. And what it really connotates is that it's going at super high speed to detect the short-lived peak of the signal. And that's available on all the units, and it allows you to pick up the peak power. And the little footnote there is that and it's more details in the appendix. Peak measured power is related to peak physical power, but they're not always the same. There's a little math you have to do there. The Windows Flash app in the next two rows is has a lot of knobs to really have the most detailed measurements and feedback for your flashes, and they either allow you to do a flash profile where you actually capture that in real time, and you have the ability to save that off, or a repeating profile. If you're doing something like 10 flashes of a safety strobe and you want to integrate over all 10 of them, this application could grab the profile of all 10 and actually the integral. And then the last two rows, the ILT 2500 has built-in applets, kind of like you would use your smartphone. And the flash applet uses start, integrate, and start peak to get you the integral and optionally the profile. And then there's the beacon applet that allows you to count a program number of strobes, again, in that safety market, and it gives you the integral. It's not mentioned here, but actually does give you some detail about the peak as well. So let's roll into some examples. Measurement setup. So basics when you're doing flash measurement. All right. You want to ensure the flash or strobe power level rises well above ambient power levels. We talked earlier about it's hard to synchronize the start of that kind of randomly occurring flash and the measurement of it. It's as a result, a lot of the meters use some automatic detection to detect what is a fast rising signal. So the more that flash lives above your ambient levels, the easier it is for a meter to do that. So dark rooms, visible light, lighted room is fine for UVC, certainly, assuming that the detector is visible blind, which means that the detector doesn't see the room light like your eyes do. So it's dark as far as the detector is concerned. And then you want to position the detector as close as practical to the source. Obviously, you want the energy and the power at a particular working distance, so that will guide your testing, but the closer you can get it, the better. And then the meter should be configured. You want a fixed range, so set auto gain range to off, understanding that these meters have multiple levels of auto ranging. So this is just the highest level, turning that off and letting yourself auto range with is typically within a smaller dynamic range, but plenty for capturing flash with good resolution. And for the integrating mode, you want to do flash, which is pretty high speed, or the highest speed, or firmware peak. So these are both settings that we'll just illustrate later. And then there's your 5-volt bias is on. So you want to reverse bias your certainly your solid state photodiodes, because it lowers the capacitance and allows the actual diode to respond faster to the rising peak. As we'll discuss later, there are some modes that we use that all of these settings, certainly in the bottom half of the slide, are all done automatically for you to facilitate your measurement. When you reference the apps below, when you're using your meter or you have we refer as our Data-Lite 3 software package, this is what we're referring to. In the Data-Lite 3, there is a Windows meter app, runs on a Windows box, runs on any of these meters. This is the Windows meter, the beacon applet and the flash applet. If you have a 2500, you're going to be looking at the beacon applet and the flash applet. They have very similar behaviors. And then when you're running the other Windows application, the Windows Flash application is in your Data-Lite 3 desktop folder. It's here, it's called Flash. And the Windows Meter application, which is this picture right here, is run by selecting the meter within that folder. So we're going to talk the Flash applet first. So this is, you could be running this on your Windows desktop. You're using the meter app, or you can be running this on your ILT 2500. Important here, the applet automatically configures the meter for flash measurement. It makes it easy on you. You don't have to think about it. So when you enter that applet, again, either on the Windows box or on the 2500, you select high or low light. So this is, determines which dynamic range you're using. And I'll point out, if you select low light and take a measurement and it saturates, it'll let you know. If you select high light and it takes a measurement and the light level is too low, it'll also let you know. So there's some automation here to help you select the right range. Typically, I start if I'm measuring a flash with the highlight. And then you press integrate to start the integration. The meter will display integrate. It's doing its thing in the background as fast as it can. And when you press integrate again, it gives you the integral. In this case, 2.6 millijoules per centimeter squared. It also tells you how many flashes there were. So if you were measuring, I don't know, 100 hertz flash discharge source, and you integrated for about a second, you would expect that to read about 100. And traditionally, folks had meters from ILT to measure the energy, the joules per centimeter squared in this case, and they also had separate devices that couldn't measure energy, but they can count pulses. So with these applets here, you get both at the same time. So this pretty streamlined way to measure your radiant energy for either flashed or steady state, really any one of your sources. That's why we call it simple. Simple flash profile within the same applet. Here again, you select your high or low light, and then you select profile. And you could optionally tell it how long you want. So for 5 milliseconds, I believe that's the shortest period. If you were doing a discharge flash, that's all you would need. If you were doing an LED flash, you might have to extend this. And I think it goes maybe as high as 1 second or 2 seconds. And when you press profile, this is where, again, it's automatically detecting a rise, either gradual for LED or abrupt for discharge, above the ambient levels. So back to, you want to make sure that you're testing in a scenario where your flash or your short-lived light is rising above ambient. Next is the beacon applet. I'm sorry, it's another one of those that automatically figures the meter for you. And here you select the number of strobes to measure, go up and down on that. I think it defaults to 10, which is some of the fire safety requirements for the smoke or fire detectors. But within settings, you could set your default so that always comes up if you're doing tests over time. Select the high or low light, and notice there is a frequency change. If you're doing highlight, you could go, actually, nowadays they both go about the same, 0.1 to 4 hertz. This is just a little extra information for you. For instance, typical safety strobes run about 1 hertz, warning lights. But if you were going over 4 hertz, you couldn't use this mechanism. And a little background on that is every time it detects a pulse, it fully characterizes it and downloads it to either the meter or the Windows system. And the 4 hertz is the limitation is based on download. But in most cases for strobing lights and warning lights, 4 hertz is plenty fast enough. And then you press start, and the system will automatically just start counting the strobes and giving you the data, the integral, the peak intensity. In the end, it'll tell you the average frequency of the strobes and percent deviation, so you could see if the strobes had similar energy levels among the strobes. So a lot of useful information, and pretty simple. You start it, you stop it. Actually, you don't have to stop it. It stops automatically after measuring the appropriate number of strobes. There is a known bug. We will have a fix that this is giving you the power units that we're measuring, and as opposed to the energy units. Something to keep in mind. Now, we were talking about the applets. Now we're using some of the more standard meter functions. I guess they're all standard meter functions, but these are like more the historical meter functions before we built those applets. And these methods require you to configure the meter for flash measurement. And this is just an illustration. Gain range, you need to select, and the ranges are based on the detector current. And stay tuned. There will be some forthcoming information to show you how to map the ranges to your particular calibrated detector. Min-max mode, firmware peak. The integral mode is flash, and the bias is on. And what's not mentioned here is if you scroll down on these screens, there is a save settings, so that you could save settings so that next time you turn on the meter or bring up that piece of software, all these are already set for you. So if your life is measuring flashes and strobes, you will go set these once, you will save them, and they'll always be set for you going forward. Be my recommendation. Simple flash integration, again, that if you're familiar with it, it's that 1700 mode. You press integrate, you press integrate again to stop it. The signal automatically holds for you, and you get your answer. Here is the integral of all those strobes, or the single strobe, or a DC level of energy over time. Super simple. Start, stop, get your answer. Peak detection is very similar. Remember before we set it up the max mode for firmware peak. So you start running your signal, you point your detector at it, you press firmware peak, and this display will update every time it gets a new peak. Pretty simple. Next, we'll talk about using the Windows Flash app. Again, this is the one that it's feature rich. All right, so that's the good part of it. The what's the right word? The challenging parts, there are a lot of knobs. So these kind of go hand in hand. You want a lot of features, you get a lot of knobs. So you have to know how to set these appropriately. And usually when you first start, it's going to be a little confusing for you, but after you get a couple of flash measurements under your belt, the learning curve is fast. Detects the start of a flash with one or two mechanisms is important. It either detects the rise above a configured minimum level, which is the most common, or actually there's an external trigger the ILT 5000 has, where you could actually synchronize the start of your measurement using an external trigger. We don't cover that here, but there's documentation on this, and certainly talk to one of our application engineers if you want to do that. So when you pull up the Windows Flash app, there's a couple of items I want to point out. There's the tabs. So you could set up the flash, most importantly, the trigger. There's flash capture, flash profile, repeating profile. This is for one of those warning lights that keep flashing over time. That's the setup and the profile for that. There's a factor select. You have to make sure you're using the right factor and units that you're after. And there's a range selection. So that dials into the power range that you want to measure. Let's look at this a little more. On a range selection, this is important, and it's not called out necessarily in these line items, but the 1 milliamp, and again, we will have some tools for you, for some instruction to help convert these ranges to your light levels or your power levels. So these ranges support signals up to 250 hertz. These ranges support signals up to 20 hertz. And again, back to that 90% of all the capture are captured in these ranges 1 through 6. And in the red here, when you get to this level of sensitivity, it's just the circuit's slower. So the bandwidth is on the order of 1 hertz. So if you had a really slow, really low energy signal, low power signal, these work. They work perfectly fine. But it has to be low power, low frequency. And the auto range next is this finds the range for you and works really well with some flashing sources, not so well with other flashing sources. So in the end, we recommend you use the ranges 1 through 6. So this is a recurring theme. Make sure the ambient background power is dark relative to what you're measuring. It's best to learn the relative peak power level so that when we auto detect the start of the flash or that short-lived light, we could set the level properly. So above, remember we had that firmware peak. So that's a great peak detection mechanism you could use to figure out the peak of your short-lived light. And then you could use that and then set the minimum level for that light level capture, something below that peak. We typically start about 1/4. So if I'm measuring and I find the peak is X watts per centimeter squared, I'm going to do a flash capture at 1/4 X as my light detection, my minimum light level. You could also learn the relative peak using manual flash capture. So if you have a source that just flashes continuously, what you can do is you could set a 1 second or pick a number, 80 milliseconds, anything that is going to capture multiple flashes, and start a capture manually while the source is running. You will capture a number of flashes or strobes, and you'll be able to graph it, and you'll be able to pick out what your minimum is from the graph. And here's that setting that minimum light level. You would pick light level. You already determined what your minimum light level is, either using firmware peak or running in manual mode previously on a stream of pulses. You'll set your integration time to the shortest one you could set, because that determines how the resolution on your x-axis. And we have some examples. If you did just a flash capture, this is fast. On the system, on the embedded system, part of the meter, it does all the work for you. It gets tells you the meter, the average, the peak, the integral, all these data pieces, sends them all back. So you could get this very quickly. Doesn't save any data to the device, just gives you the answer. If you were to do a flash profile, in addition to getting everything that flash capture got, all those data pieces, it also gives you an XY plot. If I were able to scroll down on this screen, you would see all that data is below the graph here, and you could save all that data to the file. One of the drawbacks, well, you get the profile, which is nice to see. But one of the drawbacks is it could take up to 20 seconds to get all that data back to the PC in this example. So here is the same capture on the slide above, which captured 1 pulse because that was a shorter duration. But here we captured 40 milliseconds, which created a number of pulses that we were able to capture. So you get to see things like a little wobble in the peak, and you get to integrate over multiple pulses. Again, that integration time on the x-axis is programmable in the flash setup. And that's the end of the presentation there. So I hope that is helpful to bootstrap you and get you ready to go do some flash or short-lived life flashes, strobes, measurement using the ILT meters. I'm going to run through the appendix really quickly just to give you a little extra. And we'll talk about these items. So this is maybe funny, maybe not. There's a cover that comes on the detectors, and if you're new to detection and ILT, we have been on calls where maybe we get 15 minutes in and we say, wait a minute, is the cover on the detector? And people say, I have no idea what you're talking about. That cover has to come off, and you're going to see some sort of intake optic there to let the light into the detector. Silly, but it happens. This is a little illustration on the reverse bias, why you want that 5-volt bias in there. It drops the capacitance of the diode. Every diode has a capacitance related to it that slows it down, limiting how fast that pulse can rise, and putting on the 5-volt bias lowers that capacitance significantly. Relative peak. So in references that we'll get to, we have a white paper out there that goes into a lot of detail about this. But the analog front end, so that's the light goes into the detector. The detector could do a little massaging, depending on the bias and how fast that signal is working. And then the electrical signal goes from the detector into what we call the analog front end. And the analog front end can reshape the signal, can slow it down. If our circuitry is slower than the actual pulse of light, we will slow it down to get the accurate energy reading. What will happen, though, is if the radiant power rises faster than our front end can handle it, while the energy is the same, the actual peak power level, remember those slides earlier that had those well-formed peaks and decay, the peak level that you're going to see on the meter is not representative of real life. So when you're doing a camera flash or a discharge UVC flash, our peak power is relative. So that if you move the detector away at a longer working distance, you're going to see that peak be impacted. So you'll be able to measure consistency and decay over distance, but it's not the physical true peak. You have to do a little more math. You have to understand the shape of the actual curve, and the white paper again goes into a lot of detail on that. But if you're at that level, again, most people are most interested in energy, which is maintained and measured properly. If you're looking for peak of discharge sources in real physical life, you need to read the white paper and understand that. And here is an example. The orange is representative of the physical peak of a discharge source. The blue line here is how the analog front end will interpret it. Again, the energy, the area under these curves is very similar. But as you could see, the curve itself has a very different shape. This orange curve, if I collapse the time frame, would also show a tail on it, but it would come down much faster in time. And references, we talked about the Datalight 3 software. So there's a flash app and a manual, the meter app, the L2500 manual, and that flash capture app note. Thank you. Hope that helps and get you going on measuring flash, or gives you a little more in-depth knowledge if you're already measuring flash with these tools. And if you're in that 10%, give us a call. We'll help you out. Thanks again.